Our CEO Jensen was we're sitting around the room the other day, and he said, "Mark, you really shouldn't call your team that installs these supercomputers professional services because, no offense to any professional services companies in the room, but he said professional services sounds a little bit like installing SAP or something." And he goes, "So why don't we start by think of what does your team do?" And he said, IBTG. And everyone sort of stood around and goes, IBTG, what does that stand for? Well, really, it's all the stuff Paul talked about. Think about infrastructure, build, train, go. We realize there's many HPC people in the room, and not everyone is doing AI training. But even in the HPC centers, I think that very few HPC centers are not doing some AI training, so really appropriate. And the challenge, of course, whether you spend $1 million or $1 billion on your infrastructure, HPC centers, we used to joke, well, they like taking a long time to stand up the system because they're learning how to do it, so they can go get jobs at DDN or elsewhere afterwards. But again, enterprise customers and in training, there's a dozen models that are better. Every model today claims to be better than ChatGPT in some little slice. There's some announcement OpenAI is doing. They may announce some new benchmarks today in the States, but of course, everyone knows of ChatGPT because they were first, right? And so whether you're a startup, whether in any space, is you want to be first, and that difference from being first, that's going to be in a breakthrough, is going to be 100% better, 200% better, 1,000% better than what was there before, and being second and then 10% better than someone who broke through the technology. We are here at ISC, and we rarely talk about top 500 anymore because we talk so much about AI. But again, it really goes back into the infra build, train, go. One of our longtime customers with DGX SuperPod was Recursion Pharmaceutical. They installed their first cluster in 2021. They wanted to install a new DGX system. They were a little bit late getting their system. I don't know why. I guess there was some demand from some of the other customers Paul talked about. And so it was 1 week before the deadline. And they said, could you install 64 systems? Ended up number 35 on the top 500 in 1 week. And sure enough, we installed it in 1 week. So the new name of that team, we finally did come up with a name for the team, is NVIDIA Infrastructure Specialists. So you won't hear NVIDIA Professional Services anymore, but NVIS, NVIDIA Infrastructure Specialists. That team has probably installed about 250,000 H100s. That's not a statement of what our sales are. That's just a statement of what the team has installed. And again, one of the learnings is that not every H100 we ship from the factory is the same, but not every H100 that gets installed is equal. We actually have a DGX Cloud, our own cloud that we run now. And of course, DGX Cloud runs on top of either the global cloud infrastructure, or it runs on top of these new NVIDIA cloud partners. And so we're, of course, benchmarking all the clouds all the time, and you would be surprised to understand what the difference is running the same exact benchmark across the same number of H100s in different clouds. So what are the challenges? What are the challenges from deploying infrastructure for AI or for HPC? Well, of course, if you're a traditional HPC center, you've certainly been aware of these. But the purchase cycles were long. The large top 50 supercomputers typically take 6 months, a year in the planning stage, 6 months to a year in deployment. Then they have a 3, 4, 5 year lifetime. In the US, one of the first large GPU-powered super systems. The Summit system at Oak Ridge National Labs, it's entering its 8th year in production, V100 technology. But again, still very useful. But of course, in the AI space, Recursion Pharmaceutical, any startup, right, always trying to get to the next one. So what are the factors? Of course, the network type and design is a big difference. We realized that some years ago, which is why we acquired the world's best high-performance networking company, Mellanox, and you'll hear from the next speaker some of the things going on in Mellanox. Software stack. We estimate that the largest number of GPUs in the world, if we try to map what application are they running, it's actually not ChatGPT. ChatGPT and OpenAI use a lot of NVIDIA GPUs, but last year we feel that significantly greater use was driven by Llama, Meta's open source model. Why? It's open source, right? Anyone can get it. Any college student, any high school student, right, can go through, get it, download it, start running it. But we have so many different GPUs. The A100 is still quite popular in the cloud. H100, of course, is the workhorse of Gen AI. We have the H200's been announced, the B200, then the GB200 with our Grace ARM-based CPU. And now you think, how does that college student, how does that startup optimize for every single Llama, for every single GPU? So again, a lot of work that NVIDIA does in our NVIDIA AI Enterprise, really optimizing not just our own large language models, but all of the popular large language models. Here in Europe, a great example of the value and the work being done on by these new NVIDIA cloud partners. If you're in the AI space, one of the hottest new large language models the end of last year released was Mixtral, coming from Mistral. Cleverly named Mix because it's a mixture of experts type model. They were able to deploy that and get that out very quickly thanks to the use of Scaleway, a French provider. They're a French company, of course. The French are very proud of their croissants, their other items, and now they're very proud of one of their NVIDIA cloud partners, Scaleway. And so it just made sense that Mistral turned to Scaleway to train their models. As we've installed these 250,000 GPUs, Jensen goes a little bit crazy because he gets all these reports from everyone, from the customers. He goes, Mark, how do you know how good a job you're doing? Right? How do you measure it? So we have some very simple metrics that we use. Sort of a triple metric, but we look at the time to install the cluster, time to validate the cluster, time to first training. How long does it take to, all the equipment, those 1,000 GPUs show up, those 256 GPUs, those 10,000 GPUs show up. How long does it take you to get up and running in training? Why do we validate? Doesn't NVIDIA have great quality, right? Every GPU that ships from the factory is working. Well, every GPU, when it ships from the factory, is working. But then you hook up 1,000 of them, ship 1,000 of them, connect them in different ways. It's an interesting experiment. Go to your favorite cloud provider and rent 100 GPUs, if you can, right? And then count how many work. It varies. It's usually not 100. So when we acquire cloud infrastructure, the first thing before I hand it over to our cloud team is we go in and we revalidate that cloud infrastructure, make sure it works. And so for all of these GPUs, right, we know what is that time to first training. GPU availability and utilization. So, well, availability at time to first train should be 100%. That's our goal with a DGX SuperPod, with a scalable unit, 32 DGXs, 128 GPUs. You get it, you install it, we turn it over, it's all running. When we install some of these larger systems, EOS is 16,000 GPUs. We didn't wait until all 16,000 GPUs were installed. The whole idea that we've used in our SuperPod design with a scalable unit, you get the first 32 servers in, you connect them up, boom, you're off and running. How do you do that at the network level? So where you're installing a network for 16,000 GPUs, how can you be up and running when only 32 of the servers are up and running? Very careful design of what we call a distributed, at least logically distributed network core. So it can start by installing just the amount of network that you need, install those first servers, get up and running. But of course, as I said, you don't always have that 100% availability. You have some failures, et cetera. So we measure how many GPUs are available at the time that first 1,000 or every 1,000 GPUs are installed. And then we measure for our own systems utilization as those systems run through their lifetime. And then finally, time to train. Of course, if you want to say, well, what is the fastest that you can train? There's a very well-known industry standard benchmark, MLPerf. Our time to train, we don't actually measure MLPerf. One of the challenges is, every 30 days we release new versions of our libraries. So we want to have a rather consistent, benchmark that we can run. So we use one of our own internal large language models that's open source, Megatron. We have a standard test. It runs about 4 hours. It can be scaled up and down. On every single cluster that we run, that we install, before we turn it over to the end user, we run this Megatron test and we measure the time to train. That's a measure of how good the architecture is of the cluster, as well as, of course, how good it was done in installing it. Again, many advances in AI, even just certainly since ISC last year, but just from 6 months ago in supercomputing. A year ago, certainly, Gen AI was very much text-based. Today, you can generate entire videos, right? Story, and so more and more, Gen AI is really a multimodal type of application. Second, and I already mentioned this one, the evolution of open source. Because it's open, because the information is shared, we see the evolution of open source language models proceeding much more rapidly. Again, for the large, huge, general purpose foundation languages, it's going to be very hard to beat a Google, an OpenAI, right? The scale that they're training at, tens of thousands of GPUs and trillions of tokens, is just very hard to do. But in open source, why are there so many different open source models out there that each claim to be better in one slice of Gen AI? Well, again, it's great to have a general purpose language, but Recursion doesn't really care about being general purpose. They're optimizing their models for life sciences. Bloomberg cares about financial services, not everything else in the world. So I think you'll continue to see a lot more development in the open source space. These two curves here, the interesting one, the blue curve is, and again, these are log scale, is the evolution of the performance of models since 2013, since ImageNet. The green curve, notice much more steeply sloped, that's the evolution in the performance since transformer models, the basis for Gen AI, were launched in 2018. And we just see this continuing to move forward. And of course, with every new generation, Blackwell, for instance, that huge stair-step increase in performance just adds more capabilities for the models. So we launched Blackwell at our GTC a few months ago, so I won't spend too much time going over this. For some time, we've been building the largest chips possible, reticle limited. It's basically the optics and the likes is how big can you build a chip? Other people have long asked, well, is NVIDIA going to go to multiple chips, or sometimes called chiplet design? We believe that driving the single die, the single chip, as large as possible makes sense to the limit. You run into Amdahl's law, other networking communication costs, other power costs moving data off chip. Nevertheless, because we're at that size, that reticle limit size, we introduced with B200 and B100 is actually 2 dies stacked in one package. With GB200, B200 will ship with x86 GPUs. It'll fit in all the same standard HGX type of servers that are shipping today, typically 2 x86 CPUs and 8 GPUs. But we also introduced GB200. This is a follow-on from our GH100, our first Grace Hopper chip. A number of new systems on the top 500 list using GH100. Also super proud that new records, the top 2 entries in the green 500 list are GH100 based systems. No B200 systems yet on the top 500 list, but they'll be coming soon. So these are the building blocks. You'll see all server vendors manufacturing systems out of here. The complexity just continues to increase, and so if you think about this compute tray and the switch tray, how they'll be put together is they'll be stacked up in a rack, 18 compute trays, each with 4 GPUs and 2 CPUs. So you think, well, this looks like, a big SGI, SMP server of, a few decades ago. Are you going backward in technology? No, this rack actually is 18 different servers. Every compute tray is a different server from the point of view of an OS, but together it stacks 72 GPUs, 18 servers, connected with 9 NVLink switch trays. You say, well, how on earth do you program that? Other than a few, PhDs at OpenAI or Stanford or someone else who's going to program that. Very simply, you don't have to program it, right? Because of NCCL, the NVIDIA Common Collectives Library will automatically figure out with your code, should it run on the local GPU? Should it go to a GPU, another GPU in that server with the 4 GPUs? Again, all via NVLink. Should it hop over to another server in the rack that's NVLink connected? Or should it go out of the rack with InfiniBand networking or Spectrum-X networking? So again, we're building out the first of our supercomputers for internal use with the GB200, as well as building another one out with the x86 plus B200. And Paul was right. We're continue to use DDN storage for bringing those up. Before we actually ship any clusters, any supercomputers, we'll have our supercomputer built. It's part of the design process of the product. So, well, why are you doing that? Well, because it's not just the chip, right? It's the server, the software, the networking, the storage, all have to work together. We don't want to ship you a bunch of piece parts and let you assemble it at your factory, AKA your data center, right? We want to make sure that we've assembled this, built this, tested it as a product. We'll have a DGX version, of course, of this, the DGX SuperPod. But again, a number of different OEMs will be building it. The DGX SuperPod that we announced connects together 8 DGX GB200 systems or 576 Blackwell GPUs. However, we're building systems much larger than this. It can be built with DGX or with the OEM versions. There's about 9 different OEMs or ODMs that are building these GB200 systems. So here's an example of a building block The DGX scalable unit is 576 GPUs. So you install them in groups of 576 or 8 of those racks. That technology, using a 3-tier InfiniBand fabric, scales out to 8,000 or 9,000 GPUs in your cluster. Or obviously have customers that are deploying. We have 16,000 GPUs with GH200 today, and there's certainly larger systems out there. So how do you scale out beyond 8K? We're building out for some of our customers using an 1152 GPU scalable unit. With that, you can go up to 18,000 or 18K GPUs using the current Quantum 2 NDR InfiniBand. We, of course, announced at GTC, we announced our new XDR-based InfiniBand, and this includes a higher radix switch. So with that higher radix switch, makes it much simpler to build larger clusters with the same number of tiers in the fabric. So again, with an 1152 scalable unit building block, you'll go up to 40,000 GPUs, and with 2300 in Quantum 2, you can go up to 36,000. If you go above that, and we do have some customers that want to go above 36 or 41,000, there's some address limits in InfiniBand that are at about 48,000 GPUs, and so we have an InfiniBand router that lets you build clusters, single clusters that are bigger than 40,000 GPUs. So just a little example of that. One of the things that becomes very, very important is you build these systems is not just the layout of the fabric, but again, for energy efficiency and for density, all of the GB200 products are direct liquid cooled. So now you have to start thinking, importantly, of the layout of the CDUs in the system, and you need to think about the power distribution. It's about 120 kilowatts per rack. And so, again, in the past, if you were to install 1,000 GPUs, you get our design for the scalable unit. It'd have 2, 4, 3, or 5 servers, HGX servers in a rack. We have some customers deploying up to 8 HGX servers in a rack. And you go from there. With GB200, the considerations around power and cooling and the layout become very, very important. Why? Because of that utilization. You will have failures in CDUs. You will have failures in power supplies. You don't want one PDU failure, one CDU failure to take out your entire cluster or to take out large chunks of your cluster. So really, one of the things we did really learn from working with all of our CSP customers over the years, that they were very focused on this. How do you limit the blast radius? So all of that is being incorporated into our designs. Here's an example of a 16K Blackwell GB200 cluster that we're laying out. And in this case, it again uses a distributed core. In this case, the distributed core concept is a logical concept. In this case, it's applied physically and lets the cloud provider go through and build out that core one data hall at a time. Why would you do this? You know, if you come from the HPC world, you're thinking one data hall, everything shows up at once. You spend that 6 months or that time to install it. Think about it. Everyone is building new data centers as quickly as they can. These 4 data halls are about 70 megawatts in 4 distributed different halls. They're literally building one, and as soon as it's built, as soon as the physical hall is built, starting to bring up the GPUs in it. They'll take about a month to bring up a quarter of the GPUs and then move on to the next one. So again, with GB200, I think the 2 to 4x storage requirements are going to be at the low end here. And remember, people are thinking of training. Our inference, or the world's inference workload, is quickly going through and growing to be more than the training workload. And it only makes sense, right? most people are running AI models, especially in the open source world. But even ChatGPT, right? How often does OpenAI come out with a new model? Well, they may tell you later today, right? It's not that often. Once a year, a few times a year, but then there's hundreds of millions of people running it. In the open source world, right? Running Llama 3 different versions of Llama so far, and some, maybe intermediate versions, but many people running it. So the GB200 architecture is going to be an amazing architecture for running inference, and we're really thinking through today these large-scale inference, right? You have a state-of-the-art 1.8 trillion parameter model. It's not running on one GPU. In fact, it can't even run on 8 GPUs in an HGX. So that NVLink 72 or the smaller brother of that, the NVLink 36 rack, are going to be great products for large model inference. And again, storage is going to be a big requirement there. And I think one of the places where your new Infineon storage is going to play really well is, of course, the exascaler one does. So I'm over time, so that's it.